Hello, I welcome you all to this another interesting screencast. The problem reads if each of the three links of the mechanism has a weight of 20 pounds, determine the angle theta for equilibrium of the spring, which due to the roller guide remains horizontal and is unstretched when theta is equal to 0. This problem is coming from the Engineering Mechanics Statics textbook, 13th edition by R.C. Hibbeler. Alright. We are going to use the virtual work method to solve this particular problem. This is an alternative to the equilibrium of a particle method, equilibrium of a rigid body method, equilibrium of interconnected rigid body method. And if it's an alternative, therefore it means we are able to solve this particular problem using the equilibrium of a rigid body or interconnected rigid body to still find the same solution that we're going to find as we use this method of virtual work. So what is this method of virtual work? This is a method that states that the total work in a system is equal to 0. Del U is equal to 0. And this total work is contributed due to the product of a force and translational virtual displacement. It can also be contributed by the product of a couple moment and rotational virtual displacement del theta. And when we sum up all the virtual work in a system is equal to 0. Right, so given a force F and a translational virtual displacement del R, for work to be there, the two must be collinear or parallel. And if they are in the same direction, then we have positive virtual work. Otherwise, we have negative. The same applies to a couple moment and the rotational virtual displacement del theta. They're supposed to be parallel or collinear for us to have work. And if both are in the same direction, then we have positive virtual work. Else or otherwise, we have negative. So this is about it in brief about virtual work. So first things first, we need to draw the free body diagram. After we've done the free body diagram, then we apply a virtual displacement and then draw another diagram of a deflected or displaced configuration of the same system. Then later on, write down the virtual displacement equation, which later on we feed in our virtual work equation to solve for the unknowns. Alright, so the free body diagram first. There we go, a hinge here at this point. We are going to label it. It's not labeled, let's call it A. We're going to call it A. So this will be A. The other hinge, we are going to call it B. Okay. And then what else? We've been told we have the weight, which will be acting at the centroid of each one of these members. We have the weight. We've been given the mass. So the mass is going to constitute the weight. Alright. So let's call this as A, then this one as B, then this one C, D, we call this E, then we call this one F. I'll call both of these as F. Alright. So let me label this. This is W. It's the same W there. It's the same W. Then this is our BX. This is our BY. This is our AY. And this is our AX. Right. And then if we are to section this particular spring, we are going to have the spring force in there. We'll have a spring force like so. All right, so let's call this one as fs. So we have fs, we have fs. So have we done everything? We've drawn the free body diagram, represented all the forces, both active and reactive forces. So now we need to apply some vector displacement. You can apply it at A, B, C, D. It's really up to you. All right, for me, I'm going to apply it at D, and I'll apply it in this direction. So I'll apply it in this direction, and once I do this, the system is going to also move down here. It will also move down here like this. So once I apply it there, I will have a movement at this point down like so. Okay, let me draw it. So there you go. I apply a vector displacement in this direction like so. I'll draw the others later on. So let me call this one first. I name this one. So this one is just going to be equal to, let's call it as our del x d. That's a vector displacement in this direction. Let's draw the free body diagram for the displaced or deflected configuration. And you, the spring remains horizontal. Okay, there is this roller there that's free to move. So we are going to have a system like this. We assume we have a system like this. Okay, a system like this. All right. Okay, there we go. Okay, let me coincide it with my drawing. All right, so something like so there, and there we go. All right, so now let's draw all the vector displacements that we have. So like we said, at E we have this movement like so. We also have this movement like so. Okay, at F we have these downward movements like so, and we have this movement like so. Same applies to this point. We have this movement like so. We have also a downward movement like so. Of course, at C we do have all the movements are everywhere. Even here at A, even when we apply this, we are also going to have a movement like so down there. All right, we have all these vector displacement. We have rotations. At A, we have this rotation, but of course, we don't have any couple there, so we don't expect we have this rotation. We have this rotation, and so on. Can call them del theta A, del theta B, and so on. All right, but we are interested in the points where we have forces. So let's name this. This one is just going to be equal to del y e. Okay. All right. Let's name this. This is just going to be equal to del y f. Okay, and this is the same there. All right, and then this one is del x f, and it is also the same, this one and this one. All right, what else? These are the ones basically that are going to cause virtual work, and those are the ones we are interested. So let's pick our reference. Let's say our fixed reference, our fixed reference is A. Let's pick A. So once we've done that, then we can start now indicating the location. So from A, since we have a movement in the horizontal, we are going to do this like so, that point. All right, and also from this point to again from A to F, of course, again from A to F upwards, we have this movement like so. Okay, F, there are two of them, and then we have from A, we have this one from A to E. No, from A to E is in the vertical direction, so we can draw like so. From there to there. Alright, there we go. I think this is about it. We've drawn that one in that direction. We've drawn this. Now we have another one. We have another one which is we have another one from which one? Okay, that one. All right, I think this is about it. Okay. All right, let's just now work on our drawn figure. Okay, there we go. Great. Let's label these ones. So this is just going to be equal to this one here. It is y. This is yf. Okay, steering with the movement in the vertical direction. This one is x. This one is x f. We have a movement in the horizontal direction, which is going to create a virtual work with the spring force. And then we have this y e. All right, this is about it. Let's define our spring force. We've been told that, of course, we know that spring force is equal to K, which is the spring constant times the stretch, and K is already given. What is K there? It's 50 pounds per feet. All right, and S is just equal to L final minus L original. Of course, we've been told that L final at theta is equal to 0 is unstretched. Of course, it has its own original length, which we can call L. But when we do the subtractions, they'll cancel out, so we can just say L naught is just equal to 0. Okay, 0 feet, 0 feet at theta equal to 0. Okay, degrees. And then L final is therefore going to be equal to when this is stretched, then we'll be looking at this difference, which is xf, and this one is just going to be equal to, what is the angle? Where is the angle here? Where is the angle? I can't see the angle. Okay, there it is, this angle there. This is the angle here. Let me just indicate it there. I indicate this angle here. It was not visible. All right, so this is the angle. This is the angle, which is theta. All right, so L final, therefore L final is just going to be equal to is equal to half the length of this member. What's the length of this member? Is 4, so half is a 2, then 2 sine theta, right? Okay, so this is the final length, which is just basically also the stretch. All right, great. So therefore Fs is just going to be equal to 50 times 2 sine theta minus 0, which is just equal to 100 sine theta. So we have Fs. Let's define this particular length. xf is just equal to 2 sine theta. Therefore, the vector displacement del xf is just equal to 2 cos theta del theta. Alright, and then we have yf, we have two of them, so we'll say 2, and this is at half the length, so 2 the length there, cos theta, okay, which is basically equal to 4 cos theta. Therefore, a del yf is just equal to minus 4 sine theta del theta. Because we are interested in the modulus, this gives us a 4 sine theta del theta. Alright, then we have ye. Ye is just equal to ye is equal to the full length, which is 4 cos theta. Therefore, the vector displacement y del e is just equal to minus 4 sine theta del theta. Because we are interested in the absolute value, so that this is just equal to 4 sine theta del theta. Then let's now apply all these vector displacement in our vector work equation del u equal to 0. Okay, let's start. Of course, at A, no vector work. At F, we have two of them. This in the horizontal is negative. The spring force is in the opposite direction with the displacement. So we'll have minus Fs del xf. Okay, and then at the same point we have in the same direction w, and there are two of them. We've already accounted the displacement in both cases, and therefore because they're in the same direction we have a positive, so this is just going to be equal to w del yf. And then at point E we have another w there, so this one is, they are both in the same direction, so we'll have in the vertical direction, so it will be plus again w del y e. Okay, so equal to 0. So let's replace these values. Let's do it up there. Okay, so let me just calculate w, so that I do the replacement up there. So w is just equal to, this is equal to, we've already been given, it's not in kgs, it's in pounds. Okay, w is already given. All right, so let's go up there so that we work with this information given. All right, so we have those equations. Let's write them now. So we have minus fs, and fs we said is equal to 100 sine theta. Okay, del xf is going to be equal to 2 cos theta del theta, and then we have plus w is a 20, it's already given, so w is equal to 20 pounds, right? Okay, so 20 times del yf, which is just a 4 sine theta del theta. This accounts for the two cases on this one and this one. Okay, and then we have another one which is a 20 by del ye, and this is also a 4 sine theta del theta equal to 0. So let's work out this now. So we have del theta, factor it out, then we can begin to sum up everything. So this one just becomes a 200 sine theta cos theta. Then we have the other ones, which is a 20 by 4 by 2. Okay, so this is negative and this is negative. So minus 200 sine theta cos theta, then plus 160 sine theta. Okay, equal to 0. So del theta we know is not equal to 0. The only part that will be equal to 0 is this part. Okay, so let's get rid of sine there. We can divide through by sine and write that. So it becomes just a 2 minus 200 cos theta plus 160 sine theta equal to 0. No, sorry, the sine, we've gotten rid of the sine. Minus 160 equal to 0, right? Cancelled out the sine. So writing this just becomes cos theta is just going to be equal to 160 divided by 200, and therefore theta is just going to be equal to, so 160 divided by 200, cos inverse of that we have a 36.87 degrees. Okay, 160 divided by 200, cos inverse of that 36.87. Right, I think this is about it. We found the angle. That is required for equilibrium. I hope this particular video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.